Okay, welcome everybody. I am Jim Knoll from the Tucson Amateur Astronomy Association, and we're going to have a great night of some deep sky observing. With me tonight, I've got four other TAAA members, and then we also have two members from the San Diego Astronomy Association. So once we start showing some objects, when they show their first one, they'll just say a few words and introduce themselves as we go around the horn. So Bernie, why don't you go ahead and share your screen? And hopefully you guys are seeing this on Facebook fine, but if you have any questions, feel free to type them into the chat. And if you have any objects that you'd like to see, let us know that as well. And definitely go ahead and let us know where you're observing from, where you're watching from. We'd love to kind of get an idea about that. All right, so with that, Bernie, I'm going to turn it over to you and you can talk about this first object. Are you ready, Bernie? Oh, you're on mute.
There we go. How's that?
There you
go. Good evening, everybody, and welcome this evening. We've got some nice objects for you to look at. We're going to start with the object that I have on the screen right now, and that circular object that you see faintly in the center of the screen there is called the Helix Nebula. This is a planetary nebula in the constellation of Aquarius. Now, I'm in Tucson right now, so it's fairly down low on the horizon. It's only about 25 degrees above the southern horizon. But it's coming through fairly well tonight. And let me tell you about the Helix Nebula. It's also called the Eye of God. Not sure where that nomenclature came from, but that's one of its other known names. In astronomy, it's also known as NGC 7293, which is the new general catalog number for it. I know that's exciting, but we have to number these stuff as well. This object was discovered by Carl Ludwig Harding in 1824. Now, that's actually a little late for objects to be discovered. Most of the objects in the sky, like planetaries of this sort, were discovered in the 1700s. And the reason why this one was a little later on is because it is a dimmer object. It is harder to see, and it requires a much larger telescope, or in our case, an average size telescope with a camera and some integration time. It's about 655 light years away. Now, that might sound like a long ways away, but that's actually fairly close. And this is one of the closest planetary nebulas in our sky. Planetary nebulas are actually a star that is blowing off shells of its outer atmosphere. So if you look closely, right in the dead center, and I'm going to bring my mouse over there in case you can see my mouse, right in the dead center there is the star that is responsible for this nebula. So over time, this has been blowing off shells of its outer atmosphere. And the furthest shell shown here is about an 11,000-year-old shell. So about 11,000 years ago, this star started blowing off its outer shells. Now, the furthest most shell, you'll notice, has a red tinge. And the reason for that is because that's hydrogen gas. The star is ionizing that gas and causing it to re-emit in its perspective wavelength, which is around 6,000 angstroms or so. And therefore, it's giving off a red appearance. That's the hot hydrogen shell that was blown off. Now, you'll also notice just faintly on the inner side of it, there's a bluish green coloration as well. And those were probably some shells that blew off later on. And most likely those are oxygen, possibly some other molecules, but I think oxygen is the predominant one. I'd like to turn it over to anyone else that'd like to add anything on to the Helix Nebula.
Oh, think you mentioned it, Bernie, but I believe the Helix Nebula is one of the closest planetary nebulas to us.
I did.
Okay, good. Yep. Yeah, that's a tough one to see visually. As you can see, even with Bernie's camera, it's pretty faint. But it shows up with some beautiful colors and things like that through the camera. Okay. Well, thanks, Bernie. All right, how about over to Jim? You ready to do yours?
Sure am. When I can share the screen here. And I always forget it's 2 keystrokes to do that. What I'm looking at right now, and in a moment I'll expand the picture a little bit, at least for me to see it right. What I'm showing right there is called an open cluster. And the cluster itself, an open cluster is an item that is formed from a single gas cloud. And that single gas cloud starts forming stars that all hang out together because they were out of the same local area. But eventually they will start to expand. And what they do when they expand is get farther apart and they lose the picture that they are. So, while I'm fooling around there we go. That item, that item has a couple of names. It was discovered in 1783 by Caroline Herschel, just 2 years after her brother William Herschel had discovered the planet Uranus. But they kind of worked together she helped do the math and he did a lot of the observing because he was trying to build mirrors. But right in the center of the screen is the other name for, she named it the rose cluster because she thought the center of it looked like rose petals, a group of rose petals. But it later, with people with a more artistic kind of name, they called it the screaming skull. Now that's kind of hard to see, but I'm going to try to activate a tool that'll let me show it to you. And let me get that there. If it will. Well, I'm not going to draw it this time. But right in the center, there's an open mouth. There's a jaw going up to the top of a skull. and there's an eyeball and an eyeball. It became known as the Screaming Skull or the Ghost Cluster. But it ended up picking up its original name of Caroline's Rose when she first named it. So that what I'm going to try to do here is say the cluster she thought she had 150 stars in it. When people got better instruments and the ability to look just 2 seconds longer, I'm imaging that for about 2 seconds right now. I'm going to go out to 4 seconds and we'll see what the real nature of this cluster is. There's 1,500 stars approximately in this cluster. So you need extra equipment to see that the thing. Now, it turns out that this object is about 7,500 or so light years away from us. It's 35 light years in diameter. At low exposure, it seems to be the rose petals or that skull, and you can still kind of see the skull in the middle of it. But the actual cluster is a little bit bigger than my screen displays. So this is quite a populous cluster. But the age is what's amazing about it. Most clusters last, somewhere around from their formation for maybe 100, 200 million years. That would be a time to expect all the stars to drift away. This is 1.75 billion years old. And the reason it's so old is there's so many stars formed out of that cluster, the gas cloud, that their own gravity is holding them together. And so that was Caroline Herschel's discovery, and she worked closely with her brother on astronomy. She ended up being one of the best educated mathematicians in the 18th century, and she won many awards and actually developed many of the catalogs. This is in the new general catalog item number 7789. And her mathematics went into that 100 years later when the new general catalog was being established. And it's just a wonderful object. The more power you put on it, or the more integration you put on it, the more of the 1,500 stars you could see. Any questions?
No, that's great, Jim. Yeah, that's a beautiful cluster to look at, and it's good to see Caroline Herschel getting involved with it. So yeah, that's awesome.
Yeah, she did discover hundreds, at least, planetary nebula on herself, many, many clusters, and a lot of other objects. And she greatly assisted her brother with the math and to do all his exploration. And then her nephew, John Herschel, later in the mid 1800s. She started this work when she was 22 and she lived to be 96.
Very good. All right. Let's cruise on over to Rick and let's see what Rick's got on his scope.
Yeah, greetings everyone. This is Rick Paul in Tucson. Let me get this up here for you. So what you're looking at here, now my objects tonight are going to have a spooky Halloween theme to them. So this is known as the Witch's Broom. The Witch's Broom is up in the constellation Cygnus. It's what's called a filament of the greater Veil Nebula. The Veil Nebula is also known as the Cygnus Loop. This is a very large object in our sky. It's very dim. It's very hard to see. It takes a telescope with a very big telescope or a telescope with a camera to see it. It's part of a supernova explosion that happened somewhere between 5,000 to 8,000 years ago. It's relatively close to us. It's about 2,600 light years away. Now, you'll see a bright star there in the middle of it. That bright star is part of the Cygnus constellation, and it's actually much closer to us, where the nebula is, over 2,000 light years away. That star is only 200 light years away. So the star is actually having no impact on the light of that nebula. But if you were to see the entire Veil Nebula, you could kind of see that it's kind of the shock waves of an explosion that happened, these layers of gas that have come off of it. So that is the witch's broom. Anybody got anything to add to that?
Very appropriate for this time of year.
I like how you
Yeah, and
got
that's
the additional nebulosity in the upper right there too, Rick. That's a tough one to pull out.
Yes, yes. I've actually got, for everybody, I've got what's called a narrow band filter on my camera. It filters just very narrow band waves of light in which these gases and these nebulas, that's the light they're emitting. So that helps pull those colors out. So you've got the main witch's broom here in the center. Then you're seeing the rest of this nebulosity on the right is some of the rest of the western side of the Veil Nebula.
very good. All right, thanks, Rick. I'm going to go ahead and stop your screen share. So we're going to switch over to our San Diego group here in just a minute. But before we do that, I want to introduce David Levy from the Tucson Club as well. And David's going to say a few words. And David, feel free to chime in on any of these objects as we're going along as well.
Thank you. Thanks, Jim. And it's good to be here. I'm hoping that our grandchildren are on Facebook right now, Summer and Matthew. I'd like to welcome them and all of the rest of you. And I want to thank Kyler Diggs from Channel 9. He is for pushing and promoting this event tonight. He is a wonderful meteorologist, very professional, does very good explanations of the weather. He is highly regarded in the community for the accuracy of his forecasts and the ease with which he explains them. And I'm really very pleased with that. Also, I'd like to welcome our San Diego astronomers tonight. I gave a lecture at the San Diego Astronomers years ago. I'd like to come back there at some point. It'd be nice to see my old friends there. I'm going to quote not a picture tonight, but a poem. And the one that I chose is, I think, appropriate. And I think the poem that I'd like to do tonight is rather appropriate for Halloween. It is from Robert Frost's book, The West Running Brook, which he published in 1928. And the poem is Acquainted with the Night. I'll try to add a bit of a Halloween tinge to it. I have been one, acquainted with the night. I have walked out in rain and back in rain. I have outwalked the furthest city light. I've looked down the saddest city lane. I have passed by the watchman on his beat and dropped my eyes, unwilling to explain. How many of us have actually experienced that? I have stood still and stopped the sound of feet. From far away, an interrupted cry came over houses from another street, but not to call me back or say goodbye. And further still, at an unearthly height, one luminary clock against the sky proclaimed the time was neither wrong nor right. I have been one, acquainted with the night. And thank you, Jim, and back to you.
Awesome, thank you, David. That was a gorgeous poem. We're fortunate that David's a member of the club and he can give us some good information and tidbits and some of the great stories over the years of some of his observing quests. So very cool. All right, so let's switch over and why don't we go ahead and do Dave from San Diego. You're up.
Okay, great. This is a great opportunity for us to get together with another club and share this kind of interesting experience. I'm fairly new to imaging. Gary, my partner here, got me started last summer when our outreach program had pretty much collapsed and we had to decided to go get into the virtual environment. So it's really cool. Jim, I met you at what was left of the Grand Canyon Star Party this year, and had a great time. Really enjoyed our company there and all the experiences. So yeah, I really enjoy that. Tonight, I am, let me share my screen here real quick and see if I can get what I want. This one, share. And I see I have a satellite. All right, that's fine. Anyway, I am using a little Celestron 6-inch mid-cast range C6 using an f6.3 reducer. And I have a QHY 294 color camera, which is not well matched to this telescope because it vignettes really terribly. So I am using a crop screen on this image here to keep it under control. And until about maybe 60 seconds ago, we did not have this nice satellite going through my stacked image. So this is stacked, by the way. So for the all of our observers out there, this is a globular cluster. It is known as M30. This globular cluster, it's in Capricornus, pretty close to Jupiter tonight, actually, a little bit below it. And this globular cluster has, about 200,000 stars in it. And it's a very interesting one for me because looking at this cluster in different ways, you see different patterns in it. And to me, that was, from a visual perspective, I've observed this in my 16-inch Dob, and it really is fascinating to see the patterns that you can see in a visual scope. And I can demonstrate some of that here in a minute. So this cluster, globular cluster, has a very dense central region, and it has a sort of faint haze of stars around the outside of it. It also has 5 or 6 arms that I'll show you here in a minute that are kind of interesting to look at. And in a way, it sort of looks like a pinwheel when you change the exposure on it. So, or maybe a sparkler or something like that. It's pretty interesting. The arms are bent and some are straight. So it's a very fascinating kind of thing to take a look at. One of my favorite authors in this area of observing the sky is Stephen James O'Mara. And in his book regarding M30, he says that this globular cluster looks like, or the nucleus of it looks like a very active comet. He thinks it looks like a comet with trailing arms coming off of it. So it's very interesting to take a look at. Let me see if I can show you what I'm talking about. I'm going to change the, I'm going to stretch this a little bit less. Here we see the whole, basically the whole globular cluster in the center. And if we change this a little bit, what we're going to see is the very dense central core and some of these very interesting arms that are trailing off of this thing. I can see 4 of them easily here tonight in this image. And this is what makes it so fascinating. When I'm looking visually at these objects, I tend to sketch them. So I watch them for, half an hour to an hour and look at them in different ways and find all these interesting, cool patterns in it. So it's really cool. So the reason this globular cluster looks this way is it has undergone what has been called a sort of a core collapse of the cluster itself. Or actually, I think the term they use is mass segregation. So the heavier stars in a cluster have been drawn into the center to make this nice dense core. It's sort of like what happens to a star when it begins to collapse and the core gets very dense. Well, the same type of thing, not the same exact thing, but the idea of the heavier items moving to the center of the core seems to be what made this very dense core-looking object. So there's actually quite a few of the globular clusters do have this mass segregation feature where the core is sort of collapsing. It's not like a violent collapse; it's just sort of a migration towards the center of the core. But it's very interesting to take a look at. And when we go back to the different look at it, we can see the haze of stars, the larger haze of stars around the outside. And that's, to me, it's a very beautiful, bright cluster to take a look at. I have a couple other clusters I will be looking at later on. And I want to show that, sort of demonstrate the difference between a globular cluster and an open cluster. They are completely different items, and we can talk about those things. And if we have some time, we'll talk a little bit about where globular clusters may have come from. It's still quite a mystery, has not been resolved, and so we can talk about that later on if we have a chance. So anyway, let's see if we have any questions. Jim, do you see anything there?
No specific questions on M30. You did, talk a little bit. It's globular clusters. I don't know if you mentioned it, Dave, or not, or some of the older stars in our Milky Way galaxy, but you can kind of get into that discussion of the differences when you show the open cluster later on and how they look differently. I always enjoy looking at globular clusters because they all have their unique appearance. They all look different.
Yes, and when I have a chance to show one of the open clusters, I wanted to discuss the huge differences between these two. Even though they use the name cluster, they are completely different kinds of objects. And I hope to get into that if we have a few minutes to do so.
Okay.
So anyway, that's about it for now.
All right, thanks, Dave. Before we turn it over to Gary, we did have a question earlier on Rick's image, the different colors in the witch's broom. They were asked if those colors were just different gases, and that's basically what they are. So oxygen will show up different than hydrogen, than other gases that are in the particular nebula that we're looking at. So they all can show up as a slightly different color. And astronomers can actually, the professional astronomers will actually, they can assign certain gases to a color. And so they can use that to really kind of glean out what's going on within the particular nebula. Okay, Gary, you're up.
Okay, great. And welcome everybody on Facebook. My name's Gary Hawkins. I'm with the San Diego Astronomy Association. And I'm actually going to start with a blank screen. And while you're looking at this image form, perhaps you can try and guess what it might be. So I'm going to screen share. And hopefully can you see my screen there, Jim?
Yes, we can.
Perfect. So as you can see, I got a pretty blank screen here. The image that's going to come up is going to come up here. And I'm going to start what's called a live stack. And I'll explain what that is. So I'm going to let this live stack start. I've actually got the telescope, which is an 8-inch Celestron telescope. Set on the target already, it's positioned correctly. And I'm going to be collecting images about every 15 seconds here. And what the program is going to be doing, and in fact, what everybody's program has been doing, is we're taking these individual images and we're adding them together. And what this does is it basically improves the signal to noise ratio of the image over time. So the longer we do this, the more information we can extract from the image. And I've already captured a few frames now. You can see I've got about 45 seconds worth of data. So that's 3 images. And for those of you that are looking at the screen now, it might actually be possible to guess what we're looking at. And if you haven't recognized it, I will explain it in a few seconds. But just to sort of paint a little bit of a picture about where Dave and I are, we're actually located in my backyard, which is about 30 miles east of the city of San Diego in Southern California. It's a pretty entertaining evening out here. And apart from getting a little bit chillier now as the sun's gone down, we've got a lot of dog noise around us. The coyotes are screaming in the background on occasion. And we're pretty much looking at a dark sky out here on the patio. I think all the guys from the Tucson club are probably running their telescopes remotely. We're actually both sitting next to our scopes. And so I thought I'd start with something that was actually outside of our own galaxy, and in fact is another galaxy. It's a galaxy with the designation M33, which is Messier Object 33. And this is the Triangulum Galaxy, sometimes incorrectly, or certainly referred to sometimes as the Pinwheel Galaxy, which is a name that's more associated with M101. But I think you can see from this image that we have forming on the screen here why it might get that name. You can see if you follow my cursor around on the screen, which is hopefully showing, you can see these spiral arms coming out. And this actually shares it shares the shape with our own galaxy, the Milky Way. Our own galaxy is also a spiral galaxy. The difference between these two galaxies is our own galaxy is called a barred spiral galaxy. It actually has a denser central region to it. And we're actually looking at this galaxy pretty much face on. So if you kind of imagine the galaxy as a dinner plate, we're kind of looking right down on the top of the dinner plate, except for it's not a circle, it's more of an oval in shape. And to give you an idea of just how the size of this object in the sky, if you could actually see it, my camera, my telescope setup here has a field of view of about 1/2 degree from left to right and up to down. And if you were to image the moon would just about fill the screen and almost touch the corners, or almost touch the edges, I should say, as a big circle. So if you could actually see this galaxy, and you can't because it's pretty faint, it would actually be a really impressive object in the night sky. And in fact, the galaxy itself is about 4 times the surface area of the moon. If we were to allow this long enough to form, and we could see more detail coming out in these spiral arms. And I have a fairly complicated control panel in front of me. One of the things I'm able to do with this control panel is I can adjust some of my light positions here. And that allows me to bring out certain parts of the diagram or the certain parts of the image more clearly. And I've increased, I've stretched the image here a lot more by pulling this center bar to the left. And albeit that I've created some noise on the edge of my image, I think now you can really start to see these spiral arms spinning out from this galaxy. This galaxy is the 3rd largest of what's called the local group of galaxies, of which the Milky Way is one. Andromeda, which I believe we're going to be imaging later on this evening, is the largest galaxy in the local group. And this is the 3rd largest. It's actually 3 million light years away. So the light that you're actually seeing on the screen this evening emanated from this galaxy 3 million years ago, and it's taken that amount of time to travel across space. The other thing is, when you look at this galaxy, you'll see a number of stars. These are not stars in the galaxy itself. These are stars that are in our own galaxy, the Milky Way, and we're looking past them, and they're all relatively close. We're looking past them at the galaxy beyond. And in fact, with this telescope, it's impossible to discern individual stars within the galaxy itself. And what you actually see is the stars form basically just an area of light. This is home to about 30 to 40 billion stars. And because of its shape and its spiral arms with a number of nodules in it, it happens to be a pretty favorite target for astrophotographers. Okay, Jim, I think I'm going to hand it back to you. And I think, yep, I'm going to just give me a second here. Here we go. I'm going to hand it back to you, and I'll take any questions if there are any.
All right, no specific questions right now, but I do, and Gary, while you're still up, we do want to make sure that we give a short summary of the equipment we're using. So why don't you go ahead and do that? And then when we switch it over to Bernie, you can do the same thing, and for the rest of you guys as well.
Yeah, sure. So I'm using a Celestron C8 Schmidt-Cassegrain telescope. So basically the same telescope as my colleague Dave, except for a 2-inch larger aperture. It does use a focal reducer so that I can use less exposure time and give me a slightly wider field of view. I'm using a ZWO ASI 553 color camera, which gives me a 9 megapixel image, and everything is mounted on a EQ6R Skywatcher mount, which is an equatorial mount for those that don't know.
All right, and Gary, there was a question about the spiral galaxy. Does it collect stars as it spirals? If you want to talk a little bit about that, you know, as it's rotating.
Yeah, so the spiral arms are formed because the velocities of the stars within the galaxy are different. The core in an angular sense is moving faster than the outside. So what we actually see is over time, if you could actually see if you could see this galaxy develop over time, which of course is a huge amount of time in human terms, you would actually see these spiral arms develop as the different velocities of the stars within form this pattern. So this pattern will change over time, but it's being caused by the fact that the stars are all spinning around a central point and their velocities are different.
Okay, and you know, a galaxy, just like the clusters and a smaller scale, you know, gravity is part of the feature, and so it can, you know, if it were to come across some lonely stars just kind of floating around out there, obviously it would collect them, and they could become part of the galaxy. And same with the globular clusters and some of the open clusters, or when galaxies do merge with each other, then they usually will then, you know, merge into a larger galaxy. So yeah, gravity, the central massive black hole, the dark matter around the galaxy, all that plays into the galaxy structure and holding it all together. Okay, thanks, Gary. So now we're going to turn it over to Bernie. He's going to show his next object, and he's also going to show what it looks like when his telescope slews from one object to the next. Over to you, Bernie.
Thanks, Jim. Okay, let's see. Let me show you a picture of my telescope. We'll start with that. Here's the scope I'm using tonight. It's a Celestron 8-inch scope. It's the orange tube on a Celestron AVX mount. The section in the front is a dew shield, but underneath that dew shield is what's called a hyperstar lens. And then my camera sits on top of that lens. Now the hyperstar lens allows the scope to be modified to be f2, which creates a very fast optical system. It's very quick in gathering light, and it has, as an additional benefit, a wide field of view, of about a 3-degree field of view. So I can go after really large objects like the one that I'm going to do next. All right. So the next thing I want to do is go back to my screen. There it is. And I should be back onto the Helix Nebula, which I was showing you originally. Now, to change to another object, what I'll do is I'll turn off the stacking, which Gary was telling you about. Gary and Dave were discussing. And now I'm going to tell the program here to slew to my next object. So I'm about to do that, and here it goes. So you'll notice on the screen, there'll be lots of little flashes of light. That's the telescope rotating around to the next object. And as it goes by stars, you see them flash through the screen. So it's working its way over to the next object, which is M31. Now, M31 may not mean much to you, but M31 is the Andromeda Galaxy. So I'm going to, now that we're there, I'm going to bring up the exposure just a little bit more. I think we can tolerate a little more exposure. And maybe even a little more than that. Just about there. I think that'll probably do it. Okay. Now I'm going to stack a few of these and improve on the signal to noise ratio. And that's how we do it. It's that simple. Looks simple anyway. For those of us who have done this for a few years, it's simple. For someone starting out, it is really difficult and it takes a lot of practice. But on the other hand, that's the fun part of the hobby. Gary, as you've mentioned earlier that you thought maybe we were remote operating, and yes, I'm about 30 feet from my telescope, sitting outside here in Tucson on a balming night, and it's probably 80 degrees out. Okay, for those who don't know what this is, and just about everybody does, this is the Andromeda Galaxy. And the Andromeda Galaxy is our closest neighbor galaxy. It's approximately 2.5 million light years away. So that sounds like an enormous distance, but all other galaxies, for the most part, all other galaxies are much, much further away. Gary, I don't remember if you mentioned the distance to M33. I think that's around 30 light years, is it? Something in that range?
It's about 3 million light years. So it's about probably about
3.
700,000 light years further away than Andromeda.
Okay, it's closer than I thought, but still Andromeda is by far the closest of the bunch. Andromeda was discovered somewhere around 964 by a Persian astronomer who made mention of it in some ancient Persian texts of seeing a faint fuzzy patch in the sky and wondering what that was. And he made note of the fact that it didn't move.
I can't find it.
Along with M31, the Andromeda Galaxy, you'll also notice there's another one down below here. This is M110. I'm afraid it doesn't have a a given name, not that I'm aware of anyway, but M110 is another spiral galaxy like Andromeda, but it's a dwarf galaxy. It's at the same distance that Andromeda is. So even though it looks a lot smaller, it's actually the same distance away. And because of that, it's been captured by the gravity of its big sister, and it will stay kind of orbiting around Andromeda for its existence. Now, additionally, there's another galaxy here, and that's this buzzball right above Andromeda, this one right here. This is another galaxy, and that's called M33. I'm sorry, M31. M32. I'll get it right yet. I was hovering in the right area. M32. You'll notice M32 doesn't have the obvious arms that the others do, and one of the possible reasons for that, one of the theories for that, is that it actually collided with and passed through M31 in the distant past and was stripped of its outer arms. So what you're seeing is like what's left over the intersection of M32. Now M31, according to almost all textbooks, has billions of stars involved. So what you're looking at here is a core of billions of stars and additionally arms flowing around it of billions more stars. It's slightly larger than the Milky Way, something in the range of 20 to 30% larger. And according to the documents that I've read, there have been 7 recognized arm structures within M31. And you can see, obviously, here's a big one that's floating around. Here's another one coming around this side. The dust lanes are beautiful on M31. Always gorgeous to look at. Over on the other side here, you can see a lot of the outer structure of the galaxy. And keep in mind, this what looks like white fuzz is actually millions and millions and millions of stars. They're just so far away that you cannot see them. Now, the stars that you can see are actually stars within our own Milky Way. We have to look through the Milky Way, our own galaxy, to see outside of our galaxy. So what you're seeing here, these are foreground stars in our own galaxy. If you could take those away, then all you'd see would be what was left, the Milky Way, the Andromeda Galaxy. There's a region right here within M31. It's called NGC 206. It's been given a number and a designation because of its brightness. This is a star-forming region, an area within this arm of Andromeda that has new stars forming at a prestigious level, and it's brighter for that reason. One last thing I'd like to point out. Earlier, I believe Dave was showing you a globular cluster. That was a globular cluster within the Milky Way. That's one of about 150 globular clusters that buzz around the center of our galaxy. Well, Andromeda has got globular clusters as well. And if you look right here, you can spot this W formation. These 5 stars, that W, are foreground stars in our galaxy. But this, what looks like a star right here, is actually a globular cluster in Andromeda. So that's one of Andromeda's globular clusters. Yeah, globular clusters. Andromeda has over 1,000 of them. So it's way ahead of us in globular clusters. Any questions on Andromeda, or anyone like to add anything?
No, we just had a general question come up, and I'll initially answer it, and then you guys can chime in if you want to. But we did, Dave Delgado asked, and Ed kind of mentioned a little bit of an answer, but what does the M stand for? So Charles Messier was an astronomer back in the day in the mid 1700s, and he was a comet hunter. And so as he was using his equipment to scope out the comets and things like that, he kept coming across these fuzzy looking objects that resembled comets. And so he started cataloging them because he didn't want to confuse them as comets. Well, as it turns out, and there's 110 of those objects, they are some of the best night sky objects for amateur astronomers. They're some of the brightest objects that we're able to see. So it turned out fortuitous for us, because they look a little bit fuzzy for him, but all these nebulas and star clusters and galaxies and all the things, a lot of the things we've been showing you tonight are a result of what Messier initially logged, and so it turns out it's really great for us. And once a year, usually in April, we have the opportunity, if you start right at dusk and go all night long and into the wee hours of the morning, just at dawn, that you can try to observe all 110 Messier objects, and we call that a Messier Marathon. And it's quite a challenge. You have to move through them pretty fast. There's a little bit of a gap midway through that you can probably catch a few Z's, but you've got to go through them pretty quick. And some people will image them, some will do visual, and some will do sketching and things like that. But yeah, it's kind of fun. You guys want to add anything else on Messier? The other objects we look at that you'll see referred to are NGC objects, which is New General Catalog. And that's the other big catalog that we use to watch, be able to identify stuff in the computer on telescopes, as well as planetarium programs and things like that.
I was just going to add a couple other notes on Andromeda. Something a lot of people don't realize is in dark skies, Andromeda is visible to the naked eye. You can see that bright central core. And it is also visible with a pair of binoculars if you know where to look. It's a very large object in our sky. If you were actually able to see the entire extent of Andromeda in our sky, it is larger than a full moon. It is so large in our sky.
I think it's about 6 moons, to be honest.
Yeah, it's big.
It's big, very big. By the way, before we move on to the next person, I understand there was a request for the Cocoon Nebula, and I will do that on my next rotation around.
Excellent. And Rick, I think you're going to try after your next one, of maybe doing Seven Sisters. If you can get that in, that was another request.
Yeah, I will get the Seven Sisters in before we're done tonight.
Okay, with that, I want to turn it over to Dave out in San Diego. You are up.
I think Dave may have mount issues.
Okay.
In which case I will step in. This is one of the problems, particularly when you are portable, as we are. We are not using permanently mounted equipment. My equipment and Dave's was, well, actually mine was put in place last night. Dave's was put in place only this evening. And one of the issues with that is it gives you a lot of options in terms of where you might be imaging from, but it also does create problems that cables and so forth and so on are never quite in the right place. And I believe from the chat that Dave is having a few mount issues. So I will step in for the moment. And I am going to show you a planetary nebula, which I've actually been imaging for a few minutes here. So I'm going to share my screen before. Yes, I'll just share the screen. And hopefully you can see this image, which is the Bubble Nebula. Just give me an okay on that, Jim.
Good to go. Looks great.
Good. Excellent. So this is a planetary nebula, which I'll explain in a couple of minutes. But first of all, let me tell you a few things about the image that you're seeing formed. This is actually quite a difficult target to image. It's not particularly bright, and it has a lot of stars in front of it, which in a usual image of this type would kind of detract somewhat from the Bubble Nebula itself, because there's obviously bright dots of light everywhere. So I am actually using a fairly special filter in my telescope at the moment. It's a dual band, narrow band filter. It only allows through two tiny slithers of light. One slither of light is based around the hydrogen alpha emission line that we see commonly, which is typically a red color. And the other one is based around the O3, which is one of the oxygen emission lines. And this filter is only allowing that light through. The rest of the light it is blocking out. And the effect of that is that for this particular nebula, which is predominantly a hydrogen alpha emission nebula, the light continues to come through and is picked up by the camera. And all the other parts of the image are kind of knocked back considerably. So instead of seeing a mass of stars here, for instance, this star would be much, much brighter if we were looking at this with a clear filter. All these stars are a lot darker, and so consequently the actual image of the nebula itself stands out and is much easier to see. And I think you can pretty much see, and hopefully it's coming through nicely on Facebook, that the Bubble Nebula has got its name for a good reason. It is a beautiful bubble shape illuminated on one side in particular, but very circular bubble, and it really does look like somebody has blown a bubble that's floating through space. Now, in order to capture this image with such a narrow band filter, if we go over to my camera settings on this side of the screen, you will now see that I'm using 45-second exposures. And using 45-second exposures with a telescope that has a ½ degree field of view can be a bit challenging because the telescope is not perfectly tracking. So one of the things that I'm actually using at the moment, in addition to the main telescope, is I'm using a secondary telescope. And this secondary telescope is actually a very small telescope, and it's looking out at a wide area of the sky. And I'm running a guiding program called PhD2 that selects a set number of stars from the secondary scope. And it is basically applying correction to the mount as it tracks what it believes to be the position of the target. And you can see these corrections taking place here, in particular on the one of the axes, which is called the RA axis. You can see that there are fairly periodic corrections, and then you'll occasionally see a correction in the declination axis. And this is making sure that the telescope is remaining well on the target, and it's making sure that my image doesn't smear when I'm using these relatively long exposures, which are typically a lot longer than you would use for this type of real-time display that we're giving this evening. So going back to the Bubble Nebula, let me tell you a little bit about this fantastic object. And again, to give you an idea of size, if you imagine the moon taking up most of that image, you can see that the Bubble Nebula and its surrounding sort of cloak is actually a fairly large object again, if you could actually see it in the night sky. It's probably half the surface area of the moon. And this particular target is about 11,000 light years away from us. And the bubble itself is 10 light years across. And to give you an idea of the size of that, the closest stars to us are the Alpha Centauri group, and they are about 4.5 light years. So this is twice the distance across as it is to the distance of the closest star to us, which is Alpha Centauri. So a pretty large object. And what's causing this? Well, basically there is a star at the center of this bubble that is ejecting material. And that material, if you like, is exploding away from the surface of the star, and it creates a stellar wind. And what you're actually looking at is the boundary of that stellar wind. And the way to kind of imagine this is, if you're next to a pond and you take a stone and you throw a stone into that pond, you will get a circle that goes out. And that is what you're looking at. You're looking at that circular boundary at a given point in time. But this is not actually a circle because it's going out in 3 dimensions. So it's actually a sphere. And as that material, which is being ejected from the star, is moving at very high velocity, as it makes contact with other molecules in the vicinity, it excites those molecules, and it causes those molecules to give off light. And they give off light at specific frequencies associated with the molecules that are being excited. And in particular, what we're looking at here is red light coming from hydrogen molecules, which are being excited and then emitting light. So like I said, this is a beautiful object. It views extremely well with a narrow band filter of the type that I'm using at the moment. And again, because of its nature, it's also one of the favorite astrophotography targets. And so with that, Jim, I will hand it back.
Beautiful image there, Gary. There was a question from Adrian on Facebook that asked, would that star eventually die?
Yes, I mean, all stars are evolving over extremely long time spans, again, relative to a human life cycle. So at some point, depending upon, and I don't actually know the exact type of star that we have at the center of the Bubble Nebula, but it is going to evolve in one of a number of ways. And as it evolves and as it gets towards end of life, it will change. It will probably eject more material. And if we were looking at this object in, say, 2 or 3 million years, when the evolution process has gone on considerably, the image that we might be would be looking at would be different to the one that we see today. But in our lifetime, which is 100 years or so, typically you are not going to see much of a change to this, if anything at all. Now, that's not to say that stars don't change on a fairly rapid basis. One of my other interests, apart from doing the visual outreach side of this, is photometry. And there are stars that you can undertake photometry on, which is basically the measurement of their light intensity. And their light intensity will actually change over the period of a few hours. And you can actually see this light change and measure this light change. And the characteristics of the light change tell you a lot about what type of star it is or what sort of star system it is. So things do change on a fairly rapid basis, but planetary nebula are not one of them.
And I assume another follow-on question that Adrian asked was that assuming the star does eventually die, which it will, then does that affect the nebula? Which it would, yes, it would slow it down.
Yes, I mean the nebula would certainly lose material that's feeding it. That being said, there has obviously been an ejection of a substantial amount, which has obviously left that star at some point and is forming this stellar wind of which we can see the leading edge of. So that's going to get bigger and bigger over time. As it gets bigger and bigger, it will obviously get fainter and fainter. And in fact, the third target that will show you this evening is a kind of larger example of it, but being formed by a slightly different mechanism.
All right, great. Thanks, Gary. Let's throw it over to Dave. Dave's going to show you M52. So go ahead, Dave.
Okay, folks. Let me get my share up here. And while I'm doing this, I've had a few little mount problems, but a couple of nights ago, I imaged M52, and here is my image. Let's see if I can get this guy up. Here we go. Okay, so this is an image I took just a couple of nights ago from my home in La Mesa, which is like a Bortle 8 sky, but I managed to get this. My theme tonight is the concept of globular clusters versus open clusters. And we talked about M30, which was a very nice globular cluster a little while ago. This is M52. It's number 52 on Messier's list. And it is an open cluster. It is in Cassiopeia area. And so this cluster is about 4,600 light years away and about 19 light years in diameter, and discovered by Messier. It sort of has, I mean, it's been described as having different kinds of concepts. Sometimes you can see a V shape in here. Sometimes you can see multiple arms that are coming off. And some people have called it, it looks like a scorpion with legs coming out. So it has a lot of interesting ways of looking at it. So this cluster is we think about 20 million years old. And the globular cluster that we talked about earlier, M30, is probably on the order of 10 billion years old. So there's quite a bit of a difference there. What's interesting is when you're looking at the open clusters, you see just a bunch of stars in an area, and they may make shapes. Some of the more, the better ones will have really nice shapes you can give clear names to, but basically it's just like connect the dots and make a thing, make an image here. And you can see that the way this looks here is completely different than what we looked at when we looked at M30. This is much, much closer. It has way fewer stars. It is much, much younger. And basically an open cluster like this are a group of stars that were formed in the same star-forming nebulosity or nebula cloud. And in that cloud, all of these stars would clump up and begin to form, and they begin to interact with each other gravitationally. Some of them are eventually pushed out of the nest, so to speak. They could interact in other ways and so forth. But generally, all of these stars are brothers and sisters, and they're all teenagers. If you think about the fact that these are young stars, they're still in and around the area of the home where they were born, where they were created. And so this is what we see with an open cluster. It is all the young stars formed in a particular cloud of nebulosity, interstellar gas. And so they're formed at about the same time. And what we see them, because they're still close together, we know that they're young. And so quite young. And hopefully, again, later on, we can talk a little bit more about the differences between open and globular clusters. But one big difference is these are very, very young and a very small number of stars. The globular clusters are very, very old and have a whole lot of stars. So I think that's a pretty good introduction right now on the differences here. Open clusters are much better understood than globular clusters because they're closer. We have a better understanding of what they are, and the stars are very similar to our own sun. They have heavy elements in them, and because there's so much like our sun, we can understand what they're doing and what's going on. So with that, I think I'll hand it back over to you, Jim, and I'll see if I can do something else.
Okay, very good, Dave. Thank you very much. Yeah, that's a good shot of a good open cluster. And Dave kind of hit the nail on the head. The open clusters typically are young. Our sun was probably born, it was born in a nebula and then was part of an open cluster for probably several trips around the Milky Way galaxy. And then as you can see, the big difference between this open cluster and what Dave showed earlier with the globular cluster is you can see that things are a lot more loose in the open cluster, where the globular was many, many more stars, tighter gravity, and so is holding together better. But as this open cluster goes around the Milky Way galaxy, the outer stars will start drifting away, and eventually the cluster will just disappear. And that's kind of what happened to our siblings that were born out of the same nebula and cluster that the sun was. Okay, I'm going to turn it over to Jim next. I'm going to go ahead and show Jim's equipment here. And Jim, if you want to talk to that, and then you can bring up M57.
Okay, there's my equipment, which looks a bit like Birdie C8, except it's a little bigger. This is a Meade 10-inch optical tube, and the camera on the back, I'm not using something that can go fast at the front like Bernie was doing. That fast meaning short time to get a big image. I'm doing a camera at the prime focus point. But the camera I'm using isn't that one. That's my super camera, and it is in the shop getting fixed, and it's supposed to arrive Monday afternoon. So in response to that, I've got a baby camera that I've been using. The camera I've been using is a third the cost of that camera that's hanging on the back there, but it seems to do some pretty beautiful images. So that's exactly where I'm sitting right now, except I'm 90 degrees different on my chair. I'm off the edge of the table so I could get some of the cables closer. And one thing I did want to mention is that it's kind of, I think, wonderful the way we can get these images, but to put things in perspective on what your eyeball does between this, your eye takes a picture about every 1/6 of a second, or 0.16 seconds. We can vary the amount of time in our images. The images I show tonight, nothing's faster than 10 seconds. But still, that's 10 seconds is 60 times longer that you're grabbing light. And not only is that the difference between your human eye and that camera, is the actual size of the opening. We're trying to grab information from a long way away. And the more information we can get, the bigger bucket we've got to catch the information, the more information we get. And so that 10-inch telescope can compare to the pupil of your eye, which is about 1/4 of an inch. So that's 40 times the aperture. And if I image for whatever seconds, I'm actually getting 240 times the number of seconds that I image in light that can be converted to viewing rather than what my eyeball can do. That's why we can look at some of these things, even something as big as Andromeda, which is 3.5 degrees. You can put it's up in the sky above the right star in the constellation Andromeda. You can put about 2 fingers up there and show it up just to your naked eye. But when you put that in a camera, you've got so much more ability to grab information and to process the information by using means that started being developed in 1602 by Galileo, was improved by Sir Isaac Newton in the 1780s with the Newtonian reflector, and then Laurent and Guillaume Cassegrain, who built the Cassegrainian, developed this kind of telescope that has a much longer focal length than the size of it. So we can make observatories a lot smaller now. Used to be the size of a building in the 19th century. If it was an observatory, was controlled by the size of the telescope. That's what made the bigger buildings. So now we can pack things tighter and we can grab a whole lot more information. So that's the system I'm working with. I've got the same mount as Bernie. I've just got a different telescope and a different camera.
Excellent, Jim. All right, go ahead and share your screen and you can show
Okay.
the ring.
Let me see what I can grab here.
You should be able to share right over this one. So just
Yeah, I
start to
can. It
share.
asked me if I wanted to be so rude, and I told it, yeah, sure.
Sure.
Okay, what I've got there is, this seems to be Planetary Nebula and Open Cluster Night. There's the Ring Nebula. Now, the reason I made that statement about my camera is this is a pretty, it's a cheap little camera, but it does pretty good, except some of the color stars you see are hot pixels in the camera because it doesn't have a cooler. But that Ring Nebula, what you're seeing, to reiterate what we've heard, a star up, and the limit is about 8 times the mass of the sun, up to about 8 times the mass of the sun. The star sort of sneezes itself out of existence. It doesn't explode in a supernova. And so what happens is it burns, it fuses the helium from the inside out. And as it does that, helium, that's like campfire ashes in there. And as it gets about 75% of that mass consumed, the gravity starts to dominate because there's no more nuclear reactions going on in the core that can actually hold its shape. So it starts to collapse. It takes the helium and combines it with the loose protons in there, and it first starts making carbon and then throws in making oxygen. Well, that extra fusion reactions in the middle make the star grow hugely. Our sun, when it gets to that stage, when it's used up about 75% of its hydrogen, maybe in about 5.5 billion years from now, it's going to grow out to about the orbit of the Earth. But it's so big, it gets cold. And that's what makes a red giant at the end of life of this type of a star. But with those helium reactions going on, it's blowing the solar wind. It's actually making the stellar wind come off so fast that it takes the oxygen and the hydrogen that's been developed and the helium, but we don't see that spectroscopically. It takes the oxygen and the hydrogen and it's blowing it away really fast. All that's left behind is the carbon and a little bit of oxygen. And so what you've got is something about the size of the Earth, a space diamond, because the newer thoughts are that the carbon crystallizes in the same form that it does in a diamond. So, but it's going to be about 500,000 degrees hot when you go out to get to it at first. So what I've got there is the Ring Nebula, and you can see the outer hydrogen, but I got a problem with this camera. This camera has very large pixels to make it work fast. And as a result, the blue-green that's on the center, you can only see a little bit of it. It's bleeding over onto the other pixels, and it's actually making a yellow kind of ring in there. So it should be a lot more blue on the middle. But that ring nebula is quite spectacular if you start taking a look at the numbers of it. That gas is expanding at 17,000 kilometers a second. And yet we haven't seen much of a change in its size or shape since it was discovered in the late 1700s. So it's blowing up, but as far as not blowing up, gotta stop thinking about that with these stars. They don't blow up, they just sort of sneeze their way out. They're not supernovas. That you have to be about 8 times as big as the sun. So this thing, let me get back to my tail here. As these gases expand, they're being lit up. The reason they're fluorescing like they are, or they're being ionized and they're glowing like they are, like a neon sign, is because that white dwarf in the center that was the star, but all that's left now is the carbon about the size of the Earth, that is so hot that it's turning out ultraviolet radiation. That ultraviolet radiation is knocking electrons off. 2 off the outer part of the oxygen, 1 off the hydrogen. when other electrons take their place, that's what snaps the color. It turns out for hydrogen, that's as Bernie mentioned earlier, 653 nanometers or about 6,530 angstroms. And there's a different frequency for blue-green, and I don't remember what it is for the 2 oxygen electrons that got knocked off, but they're constantly swapping electrons out there. And that's what makes them glow, because of the hot white dwarf. But it's going to get bigger and bigger and bigger. And eventually it's going to kind of disappear from sight. And that diamond will be out there ready for you to find. So if you're driving your space cruiser around looking for these things, watch out, because when they become black, you're not going to see them. So you've got to really be careful. You better have a good radar when you're out there flying around. It's this item itself happened about 7,500 years ago. 7,500. It was about 2,500 light years when it happened. Now, what we have to add when we throw in there, we talk about the light getting to us at 2,500 from 2,500 years ago. It's a lot farther away now. Space has been expanding. It's probably close to about 5,000 light years or more with the expansion of space. But at the time that light came out, 2,500 years ago, it took that long to get to us to see it. Space is a lot bigger now than it was back then. And it's 2.5 light years in diameter. So the diameter about, oh no, I'm sorry, not 2.5 light years. Yeah, 2.5 light years in diameter. That's about half the distance, or 2/3 of the distance to Proxima and Alpha Centauri, that are the nearest stars to our sun. So that object is fairly far away, and it's fairly old as planetary nebulas go. Usually after about 11 or 12,000 years, the gas is too far away to light up, but it still is a beautiful object in the sky. That's Messier number 57. And what Messier did in his first 40, the catalog he made of his first 40 objects, he put a forward in the book. He said the purpose he was publishing this is so astronomers would not confuse these with objects requiring study, because he thought comets were the only things important, because that was his job. He was the chronicler of dynamic events and draftsman for the French Navy. So the reason he was finding these comets was so they could predict the future for battles and for military operations. So he was superstitious about the comets, and he didn't want us to look at this stuff. It's not supposed to be worth it. I think they're kind of beautiful. And everyone looks different because the magnetic field of the parent sun, as it first went up to a red star and then fell down into a carbon white dwarf. Jim?
Yeah, I always like looking at the ring nebula, especially, you know, you can see the colors with the cameras, but you can actually see it quite clearly just visually. It'll just be shades of gray.
Yes.
But you can see the gas expanding out, and it looks great even in a telescope. Adrian asks if those gases are going to affect the outer stars, and I would say probably not, because the gas is pretty diffused by the time it expands out, and it'll start disappearing very quickly. Like Jim said, you know, most planetary nebulas are only 10 to 12,000 years old. So then the gas gets so dispersed that we can't see it.
No, it doesn't. But one thing that does is when you have a binary pair. If you have two stars, one star orbiting each other, being born together, sort of like brothers or sisters, what happens is the bigger one will end its life first. And there gets to be all kinds. If you want a PhD in physics, just pick up any one of the topics involving one binary star ending its existence before the other. But it looks like the sun was born with a giant star as a partner. That star was very large and went supernova. And the way we know it went supernova is that we can find elements of the existence of that star in our sun's outer layer. So it wasn't close enough to get damaged by the supernova, but it did get the debris from the supernova. And it's carrying it right now in the outer layer of it. So that's kind of fascinating about seeing these objects. And back when we were talking about, when Gary was talking about the comparison of globs and open clusters, the globs are sort of a retirement home because they're the oldest. But if you think about it, they've only got the average size stars in them because all the big stars have already gone supernova and gone away. You can see, in fact, in some globular clusters, if you look at them with the exact proper imaging time, you can actually see the red giants that are in there, like our sun, about to reach the end of their lives in there. M4 in particular, I like in the summer up at the Grand Canyon Star Party, because you can really find the red giants in M4. And so what we're seeing in a globular cluster is old stars, and that's what gives one of the three possible choices. It could possibly be the core of an old giant, and they found that. Kit Peak here in Arizona has done some research on globular clusters and has found several with intermediate mass black holes at the center, which is the thumbprint of a baby galaxy that the Milky Way consumed when it was being formed. The gravity of the Milky Way kind of pulled it in. But then there's others that don't have it, but all the stars are the same age. So it looks like they all formed out of a giant cloud. But then you look at some of the ones around Andromeda. Andromeda is interesting because Milky Way only has about 154 or so catalog globs, but the Andromeda has over 4,000 so far. The interesting thing is some of those stars have some of those globs have two different ages in them. So it looks like smaller clusters long ago kind of merged together from their gravity. So it's a real mystery studying globs. That's my second most favorite thing to look at after Planetary Nebula.
All right, excellent, Jim. We got to get moving along here. We're down to only about a half hour left, and we still have another round to go. So I'm going to turn it over to Rick next. Rick, do you want me to show the screen
No,
of your equipment?
I have my equipment up here.
Okay, you got it then.
Okay, let's see here. Show that, go here. So here's my equipment. I've got a different telescope than what you've seen from the other guys. I have what's called a refractor. This has lenses, no mirrors in it. This is very similar to what Galileo used. And you see on the back my camera there, it's a dedicated astronomy camera. It's cooled. It's currently cooled to minus 10 degrees Celsius. That helps lower the noise in the image and keep things looking nice and clean. So I'm going to move on to the object I have to show you here. And continuing with my Halloween theme, this is known as a dark nebula. So kind of spooky. It's an interstellar molecular cloud, and its composition is such that it's these little tiny sub-micrometer sized dust particles coated with frozen carbon dioxide and nitrogen, and that blocks the visible wavelengths of light from coming through it. So yes, you're kind of looking at smog being carbon monoxide. Now the other spooky thing about this is if you turn your head to the right, you'll see it kind of forms a letter E. And so for the Halloween theme, we're saying that's an E for evil. Now this nebula is located up in the constellation Aquila. And it's part of a catalog known as the Bernard series. Bernard went through and cataloged these dark nebulas, and he made a catalog of a couple hundred of them. So that's all, Jim. Back to you.
Excellent. Yeah, I love the dark nebula. You know, the cameras do a much better job at showing the dark nebula, and you can see visually, and the fact that that dust is just so much heavier that it's not allowing starlight to emanate from behind. So that's awesome. It's a great view. Okay, thanks, Rick. So now we're going to get back into the flow. Bernie, you're going to be next. We'll go ahead and turn it over to you if you're ready.
Sounds good. Thank you, Jim. Let me share my screen here. And There we go. So I heard earlier that there was some interest in the Cocoon Nebula. So I brought up the Cocoon Nebula here. This is a live image of the cocoon. And if I zoom in on it, keep in mind I have a 3-degree field of view here. So everything is small except things like the Andromeda Galaxy. But if I zoom in, and by the way, before I zoom in, you'll notice there is just a gazillion, that's a real astronomical term, just kidding. There's a gazillion stars in the image. And the reason for that is because the Cocoon Nebula is actually within the Milky Way itself. So when you look up at the sky, you see the band of the Milky Way. That is thousands and thousands and millions of stars in that band. And the image I'm showing you is a magnified view of that band of the Milky Way. So that's why you're seeing so many stars in this image. Now, if I zoom in on the cocoon itself, you'll notice it's red. And of course, that again tells us that that there's ionized helium going on here, and ionized hydrogen, I'm sorry. The Cocoon Nebula is also known as IC 5146. And this is a kind of a combination reflection emission nebula, and it's in the constellation Cygnus. It's an emission nebula because there's some very hot stars here that are ionizing that gas and causing it to re-emit in the red spectrum. But there's also reflection from some of the stars in the area off of the gas cloud. So there's a combination there of reflection and emission. This nebula is about 4,000 light years away, and it's about 15 light years across. So from one side to the other, it's about 15 light years. That's an enormous distance. If you think about the closest star to us, Proxima Centauri, or also Alpha Centauri, a lot of people will say, that's 4.3 light years. So, and that's an enormous distance. Well, this is 15 light years across. So a huge, huge nebula. The central star, this bright star in the center here, is only 100,000 years old, according to the documentation that I looked up. 100,000 years old is nothing in a star's life. Some stars live for billions of years. Our sun, for example, will probably last close to 10 billion years. So for a star to be 100,000 years old, it was just basically born. Now you'll notice there's some dark modeling within the nebula itself. Those are dark nebula bands that are blocking the light from reaching us. And the other nice thing about the Cocoon Nebula is that it almost looks like it has a tail. So if you look upwards, you'll notice the number of stars right around the Cocoon Nebula itself is very minimal. And then passing upwards and off to the right is what appears to be like a big black band. This is another dark nebula that was found by the astronomer Barnard, and he numbered this Barnard 168. So this is the black tail of the Cocoon Nebula. Back to you, Jim.
Excellent. Yeah, that's a gorgeous shot too. You not only got the nebula, but some of the dark lanes in there and just lots and lots of stars. So, very good. Okay, Dave, you ready for yours?
Yes, I am actually.
Okay, you can go ahead and start sharing anytime.
Okay, let me share this screen. Do you want to stop sharing screen? I continue, yes. Okay, we'll pick this, we'll share that. Okay, you got that image up?
It's good, yep.
Okay, great. Again, my apologies. The gravelly ground and my mount don't seem to be quite level and polar aligned, and that's very difficult making anything work. I should have been here maybe a half hour earlier to make sure it's a little bit more stable. But anyway, this is another image that I took a couple nights ago, and this is a globular cluster M2. So this is another globular. It's same type of object as M30 that I started with earlier in the evening. And this one, it's a beautiful, beautiful globular. I think all the globs are gorgeous when you get that sparkly look and it's in perfect focus on a dark sky. It's just like, you know, like we've heard it talked about grains of sugar on velvet. You know, it's just a beautiful, beautiful cluster. And so I enjoy these strange objects. They're so unusual. M2 is it's in Aquarius. It is currently about 38,000 light years away, and this glob has about 150,000 stars in it, approximately. And the age of these stars are in the order of 13 billion years old. So if you're studying the Big Bang Theory whatsoever, you know, that's almost as old as the whole universe, which is a very interesting thing to think about. Why would globular clusters hanging around our galaxy here be almost the same age as the universe? It's a big question in my mind. Could it possibly be? And if it is, then why is it? But M2 is one of the brighter, more beautiful clusters around, but it's really a strange cluster compared to other globulars. Of real interest is the eccentricity of the orbit. So globular clusters orbit the central black hole of our galaxy, just like everything else in the galaxy. But most of our solar systems, our sun, almost all of the matter in the galaxy is orbiting in what we call the galactic plane. So it's like a big spiral, and most of that matter is orbiting in this big flat disk that we call the galactic plane. But globular clusters are different. They don't orbit in a galactic plane. They orbit at a high inclination to the galactic plane, or rather randomly to the galactic plane. So this is like the other globular clusters. It's a fairly high inclination in its orbit, which means it's not part of the arms of the galaxy that we normally think of. And that's pretty standard for globular clusters in general. But the really interesting thing about M2 is, like I said, the eccentricity of the orbit. It's like sort of like a comet going around the sun. It has a part of its orbit is a very long ways from the center of the galaxy, and part of its orbit is very close to the center of the galaxy. So that means it speeds up, it slows down, and it has a tremendous difference in the distance depending on where it is in its orbit. Some numbers here. The farthest it gets approximately from the black hole in the center of our galaxy is 171,000 light years. And if you compare 171,000 light years to the approximate size of our galaxy, which is maybe a little over 100,000 light years, it actually gets farther from the center of our galaxy than the entire diameter of our galaxy. So to me, that's amazing that it has that kind of a high, and actually the word for that term, the word that we use for that is the apogalactic feature. So it's like the high point of its orbit. Now, the minimum, the lowest or closest it gets to the black hole in the galaxy, the paragalactic measurement is 23,500 light years. So it goes from 23,500 light years at its closest to 171,000 light years at the highest point of its orbit. So this is a very strange object that it has this highly eccentric orbit. It's a high inclination to the galactic plane, and it's to me it's just a fascinating object to study because it tells us so much about the potential of globular clusters. And Jim, did you want me to? Do I have enough time to get into a couple things about the comparison between, or should we wait until a bit later on? I know we're short of time here.
We're about out of time, but if you want to take a minute or two to do that, that would be fine.
Okay, do it really short here. Open clusters we looked at before. M2, the open cluster. They usually have like less than 100,000 stars. They have a chemistry that's very much like our sun, which contains heavy elements in their makeup. Open clusters are usually less than 1 billion years old, so they're fairly young compared to the galaxy, to the universe. And we find them mostly in the disk of the Milky Way, in the galactic plane that we talked about. These stars are all formed together in the nebula we talked about, the brothers and sisters and so forth. And we have a pretty good chance to observe these and understand them. But globular clusters, they're different. These guys have more than 100,000 stars and often have 200,000 or 300,000 stars. They do not have the heavy elements that our sun has and that most of the other clusters have. So they're lacking the heavy elements in general compared to the open clusters. Globular clusters are usually in the order of 10 billion years old, not less than 1 billion, but 10, 12, 13 billion years old. So it's really, really strange. Their orbits are highly inclined to the galactic plane. They're not in the arms of the Milky Way. And because of all these things, we don't really have good understanding of how they were formed. There are many theories, and for those of you that are interested, you should go research how were globular clusters formed, because we don't have a good solid consensus. There are possibly several ways that they came to be, but the bottom line is we just don't know. And globular clusters are beautiful to look at. Okay, Jim, over to you.
All right, thanks, Dave. Excellent discussion, good comparison. Both the open clusters and globular clusters are just fantastic to look at in any size telescope. Okay, Jim, you ready to show your next object? Are you there, Jim? Okay, maybe having some technical difficulties with Jim. So
Do you want me to
let's
take
go
this?
ahead. Yeah, why don't you go ahead and go, Gary, and then we'll come back to Jim.
Okay, cool.
Sorry, I was muted.
Okay, are you ready to go, Jim?
Sure.
Okay, go ahead.
Actually, I was chasing a cable around, so I wasn't there to unmute here.
We'll have to do this one pretty quick. We're down to about 15 minutes left.
Control, Alt, Alt. There.
And if we need to, we can come back to you, Jim.
Yeah, I'm sure. I had to remember which buttons to push.
Okay.
I was looking around the top of the screen for the share. Okay, that object is called M27. It's another planetary nebula, and it's called the dumbbell, or sometimes the apple core nebula. And that one is so big relative, because it's so much closer to us, it's so large that even if when you compute what magnitude it is, you sum up all the magnitude and its surface brightness turns out to be not so bright. So it takes a lot more, relatively more imaging time than our friend the ring did. But the Dumbbell Nebula is Messier number 27. It's in the constellation Vulpecula, the fox. That's right underneath Cygnus the Swan, if you look at it. So it's up in the rich area of the Milky Way. It was the first planetary nebula to be discovered by Charles Messier in 1764. It's thought to be anywhere from 9,800 years to 14,800 years old. And that's because of the odd shape of it. Doing it just by the shape of 1.01 light years at the sort of the middle of it, it would only be 9,800 years. But the rest of it, the bigger size in the major axis and the chemistry of the upper end of the major axis does make it look like it's 14,000 light years. So, but the one thing that's really interesting about it is the gas is flowing out 31,000 kilometers a second. And that would be the dumbbell.
Right, thanks, Jim. Yeah, and that is one, even in a visual telescope, you can't see the colors, but you can certainly see the design and the dumbbell portion of it. Okay, Gary, over to you.
Okay. Hopefully you can see the screen, and what we're actually seeing on the screen is where we left off last time. Let me just show you a couple of quick pictures. This is actually the outlook where I am today, operating from. You can see the gravel patch behind, hopefully, that Dave has been operating on and has been having problems with. And this is a much closer look at the telescope and the equipment. The one thing I will say about this type of equipment is with the electronic cameras and everything, the big difference here between this and visual astronomy is when something goes wrong here, you end up with a giant paperweight. And Dave has experienced that this evening, and sadly I was doing an outreach event to some scouts last couple of weeks ago, and this turned into a large paperweight. Anyway, moving on, let me just run through the process here of how we acquire an image. So I will go to my sky map, and you will see up here is the catalog number of my previous target, which is which was the Bubble Nebula. And I'm going to change that to my new target, which is the Crescent Nebula. And we have now selected that target, as you can see on the screen, and I'm going to slew my telescope to it. And you will see the square here moving down and around past Polaris, and the scope is slewing onto this new target, the Crescent Nebula. It's got a little way to slew, so it's going to take a few seconds here. And I am now looking back over my shoulder into the western skies, whereas the first two targets I sent you presented this evening were in the eastern sky. Now I've got to the target. But one of the problems here is if you've got a relatively narrow field of view, and half a degree is not a particularly large field of view, we won't actually be pointing at the target yet. There will be an error between where the target is and where the telescope thinks it's pointing. So the first thing that I do here is something called plate solving. And I am going to plate solve by clicking this button here. And essentially what's going to happen is it's going to take a 15-second image of the sky, and it's then going to compare that image with a database of stored images, and it's going to work out how far the telescope is in error. And you can actually see here that the offset is calculated as 0.54 degrees. And it will now move the telescope to the position of the actual target, as opposed to where the telescope was just before it did that repositioning. So now I am going to image the Crescent Nebula. I'm going to do it again using a probably a 30-second image here. And I am going to initiate guiding so that I get a stable platform. Let me just do that again. A stable platform. I'm going to select my guide stars. I'm going to start the guiding. And I am going to clear my live stack. And hopefully what we should see once the first images come through, and here we have the image beginning to form on the screen, is an object called the Crescent Nebula. And again, what I'm actually showing you is this happening in real time. So this is the first image that we see in a 30-second snapshot. The second image will be coming in a couple of moments and be stacked on top of that. But already we're beginning to see significant detail in this nebula called the Crescent Nebula. And because of the type of filter I'm using, I've knocked the stars way back. And so we're actually seeing primarily the shape of the nebula. And I will try and just do a few quick enhancements here so that we can see a little bit more detail. Here we go. And I will bring this image up full screen. And this is the Crescent Nebula. This is object NGC 6888. It's in the constellation of Cygnus. And it's another example of a star. In this particular case, it's a Wolf-Rayet star called WR136, which is shedding material. And that material is traveling outwards from the star at an extremely fast velocity. And what's actually happening with this particular star is that material that was shredded recently, and I say recently with a caveat in so much as we're talking maybe 1 million years ago, is catching up with material that was ejected much earlier from this star, and the material is colliding. And as that material collides, the atoms get excited, the excited atoms emit light, and we are looking at that light coming back into the telescope. And this creates this wonderful shape in the sky of this Crescent Nebula. You can see the main collision area where the stellar wind of one ejection is catching up to the slower moving material of the second. And it produces, again, a target, which if you could actually see, would be a very prominent target in the sky. This is only just a bit smaller in size than the moon appears, if you could actually see this in the sky. The star at the center that's ejecting all this material is reaching end of life. It's about 4.7 million years old. And with that, I will think I'll hand it over to Jim for the next person.
Okay, thanks, Gary. Yeah, that's another one that's really good in the video and images. It's pretty faint and tough to see visually, but that was an awesome picture. Okay, we're going to do one last object with Rick, and then we'll wrap things up. And I've got a couple things that people have asked about that we'll talk about as well. So over to you, Rick.
Okay, I have the object by request, which is the Seven Sisters, also known as the Pleiades. Let me get my screen shared here real quick. So I'll have to apologize for the green color here. I did not have time to remove my special filter, which is giving them kind of a green cast. Normally these have more of a blue cast to them. This is an open cluster, which means it's a very loose association of stars. They've been moving apart over time. You'll also see around some of the stars in this image, you can see some faint nebulosity. You can see some glowing around these. The nebula is actually not part of this star cluster. It is there is a nebula that's between us and the Pleiades that's giving them that glow to them. Now the seven sisters, as they're known as, come from Greek mythology. These are the daughters of Atlas, and they were placed in the sky where they are so that Orion, the great hunter, who was a bit of a lady chaser, could not chase after his daughters. So he can't reach them from where he is. They also have some other sisters known as the Hyades, which is another cluster that's nearby them, which is more of their sisters. Now, this cluster has been known since ancient times. It's very visible with the naked eye. Most of you have probably looked up in the sky and seen the seven sisters. Very, very visible. Depending on how good your eyesight is whether you can see 4, 5, 6, or 7 stars with the naked eye. They've been known by many cultures, by many names. And one of the cutest stories is they're also known in Japan as the Subaru Cluster. Well, just like the car Subaru. If you've ever looked at a Subaru, you own a Subaru, you'll notice that the emblem of Subaru is a little grouping of stars. And well, they've logoized it, but that's what it's supposed to represent, is this star cluster, and that's where the Subaru car company gets their name. So that about wraps it up.
All right.
Oh wait, I was going to
thanks,
show
Rick.
one more.
Oh,
I was going to show one more thing, Jim. I
Sure,
got a
go ahead.
second here. I'm going to switch my screen over here. Let's see. Oh, come on. Where's the share screen? So what you're looking at here now is, let's see. You should be seeing my main screen.
We're still seeing the seven sisters.
Sure. Okay, let me stop.
Okay, now we're seeing your ring.
Oh, sorry.
That's right.
We'll get it going here. Share. Okay, so here you're seeing my control setup. The system is currently imaging. It's imaging a different object right now. You can see over here on the left of the progress of it. I can see my scope position where my scope is parked, and I can see the progress on my imaging runs. I've shot 1 of 12 here. It's connected to my camera, my scope. My camera's cooled down to minus 9.5 degrees, close enough to 10 degrees below zero. But so this is how I monitor my system. So that's all, Jim. I'll hand it back to you.
Okay. All right. Excellent. Thanks, Rick. Okay, so I'm going to kind of wrap things up, and then I'll give everybody a few seconds to say a farewell from the astronomers. We did have a question pretty early on that I want to just address, and it was what tips are there for amateurs that are just getting started? And I would say probably the first and best thing to do is, if you do have an amateur astronomy club within your town or city, check them out. You can, if you're into doing some serious, if you want to, learn more about the night sky and learn more about the equipment, then I would join the club. When I first got my telescope, I spent a couple of years kind of floundering around, not sure exactly, how to use it or where things are in the night sky. And then I joined the Tucson club. And from there, I, went to our astronomy fundamentals, our beginners group, and started learning the night sky and learning how to use the equipment, and did star parties so that I'd pick out 4 or 5 objects each night or each time and learn about them. And then, eventually you'd build a pretty good repertoire of what's available. Go to star parties if the club, or if there's star parties within your town. That's definitely a great way to learn. And it's, you know, it's good to be able to look through other telescopes before you try to buy your own, so that you've got an idea of what is out there and what you want to use. We're fortunate here in Tucson, we actually have 2 great astronomy stores. So if you have an astronomy store in town, then that's a great way to kind of build the knowledge of what you want to get and talk to somebody to be able to learn, because you know, telescopes are different for depending upon what you want to do. There's a lot of great phone apps that are available for you to learn the night sky. You know, you can just download star planetarium apps, or I use what's called Star Walk 2 is a really good one. And just go out and point it around the night sky and spend some time learning about it. So there's lots of great ways to be able to see the night sky, and I would strongly suggest that you know, whenever you can, just get out and check it out. So I hope you do. I hope you did enjoy the program tonight. It's you know, it's going to be available on our Facebook page, and I'll upload it to our TAAA YouTube channel tomorrow. So if you want to go there and check it out, or spread the word and have family members or somebody else watch it later, that's fine. And I assume probably the San Diego Club will probably upload it to their social media as well. But we'll get the recording out there for them as well. So with that, I just want to say again, thanks for joining us. Our next virtual star party will be February 19th. Again, it'll be from 7 to 9 p.m. We'll be back in the mountain time zone. So that'll be the time it'll happen. So let's kind of go around the horn. I'll start with Bernie, if you want to say a few words, and then go to the next one.
Thank you, Jim. Well, I hope everyone enjoyed our 2-hour session. We certainly do. And I'd like to reiterate again what Jim said. If you're interested in astronomy, definitely find a club nearby and get involved. It's the best way to learn it as quickly as possible.
Okay, let's do Dave next.
Okay, yeah, Jim. Hey, listen, thank you very much, Rick and Bernie and Jim O'Connor and Jim Knoll. You've been a good friend this last year or so. Great opportunity to work with you guys, and we've learned a lot, and I hope we can share some more stuff in the future. Thanks for that opportunity. One quick comment on the guys that are interested in getting into astronomy. Your naked eyes are pretty good if you go to a dark sky and just look at it. And then you take a pair of binoculars and use your binoculars to explore the sky. And if you've done that for a couple of times, you'll be hooked. And yeah, then you'll be on your way. So thank you very much from San Diego. We will also have this program posted on our YouTube and hopefully our Facebook site in the next couple of days. So thank you very much, Jim, for hosting, and we hope we can do it again.
All right, thanks, Dave. Jim O'Connor.
It's always a great pleasure to get to share what we can find in our what I like to call our home universe up there, things that we might not have even been aware existed. And I thank everybody who viewed, who watched our efforts tonight. And I'd like to thank San Diego, because I arranged the astronomers for the Grand Canyon Star Party, and the San Diego astronomers have been a big group of participants for the last at least 6 or 7 years, except for the last 2 years we lost for COVID. But they're a great group of people, and I just have a whole heck of a lot of fun working with the San Diego guys up at the Grand Canyon. So other than that, I'd like to tell everybody, just keep looking up. We're too used to looking down or looking at our electronic devices. Just look at the beauty of the night sky and how it changes for us. And it can really help get you through the night.
All right, thanks, Jim. Gary?
Sure. I hope everybody enjoyed the program this evening. It was a pleasure to be doing a joint live stream with the Tucson Club. One other thing I would say is Many clubs run pretty extensive public outreach programs. The San Diego Astronomy Association pre-COVID was running about 120 events a year. A number of those, probably about 50%, are aimed at schools, but probably another 50% or so are done with our local county parks. And these are a great way to come out and see the stars, both visually. In fact, most of the telescopes that you'll see at one of those events are typically visual telescopes. And there will be a number of us as well who are perhaps doing the electronically assisted astronomy, which is what you were seeing this evening. So look out for those events. Again, it's a great way to come out, meet some people, get excited about the night sky, and then you can take the next steps to really get involved in some viewing, or if you want to go a little bit further, some more sort of scientifically based stuff. And there are plenty of opportunities to do some really valuable citizen science projects that the average astronomer can get involved with. So if that is kind of interest to you, there are some great ways to move forward in this and do some really useful work in combination with organizations like NASA and so forth and so on, with programs like their exoplanet program. So I hope you enjoyed the night sky from Blossom Valley in California, and we'll go back to the dogs, the coyotes, and hopefully a glass of something warm, because it's beginning to get a little on the chilly side out here.
Absolutely. All right. Thanks, Gary and Rick.
Yeah, hope everyone had a good time. I'll add one more thought about how to get into this hobby. If you're interested in doing, very similar things to what we've been doing tonight, YouTube is a tremendous resource. There's a lot of good YouTubers out there doing very educational videos on how to get started and set up, everything from the equipment to the processing and all of that. One I'll point you towards, easy to remember, is a YouTube channel called Astro Backyard. Very easy to remember. If you go back to, Trevor has a very easy, amenable style. If you go back to his earliest videos when he's first starting out, they're very helpful for learning about equipment and the telescopes, the cameras, the mounts, and the software and all those things. So the other thing I'll say is, if don't underestimate what you can see through a pair of binoculars. If you get an app like what Jim recommended, an app on your phone, and can find some things like Andromeda, you can see Andromeda with a pair of binoculars. You can see some of these star clusters with binoculars. You can actually look up at Jupiter and see Jupiter and its moons with a pair of binoculars. So main thing is get out there and start looking up.
Yeah, excellent. Good points, Rick. Thank you very much. Yeah, and we have all of our past virtual events on our YouTube channel as well as the Facebook page. So by all means, feel free to watch any of the earlier ones. And I hope you guys enjoyed it, and we sure enjoyed doing this, and we'll see you hopefully February 19th. Thanks, everybody.
Cheers.
Okay.